Okay, welcome everyone. So today it's my pleasure to welcome back Professor Mrozek, who will be giving the second lecture on combinatorial topological dynamics. Yeah, thank you, Marian.
Okay, so let me start with very briefly repeating the slides I started with last time. So there have been many topological invariants developed to study features of solutions of ordinary differential equations. My main interest is in a Conley index and related tools, because my belief is this had probably the most broad spectrum of applications so far. This is a traditional tool in the sense that it is just used to traditional dynamics based on differential equations or iterates of maps. But as I just mentioned, maybe already somebody listened to our conversation preceding the start of the talk. For most differential equations or even discrete dynamical systems, you have to discretize both the space and the time to get numerical experiments. So in order to use these tools, and this actually enhanced quite a lot the scope of applications, because there are now even computer-assisted proofs which combine this rigorous numerics with these topological invariants. But once you start, so since you go into discrete math when you discretize, so once you start to look into dynamical system known only from samples, then maybe one could, instead of doing what people do right now, namely they take this sample and try to build a differential equations which possibly well fits the available data, then they discretize again and use this topological tool to get the conclusion. So the big question is, would it be possible to take a shortcut? Just build a kind of combinatorial counterpart of the classical dynamical system, living in the world of discrete mathematics, and adapt these topological invariants to work directly with this combinatorial version of dynamical system. Somehow such a shortcut would be natural, but the big question is, what could be a combinatorial analog of a dynamical system? By combinatorial, I mean here finite or discrete, but I prefer the word combinatorial because people in dynamics, when they hear discrete, they typically think about discretization of time. But here I really want to live with everything in this discrete math world, so the space should be also finite. Okay, so the answer that this is possible came from discrete Morse theory. So let me very briefly recall the main points of classic Morse theory. So classic Morse theory works with compact differential manifolds. So this is just a small piece of a bigger differential manifold. And then you have a smooth function, real valued function on this differential manifold. And the Morse theory tries to relate the topological features of the manifold with the features of the gradient vector field. So once you have this smooth Morse function, you build the gradient vector field and you study this gradient differential equation, which roughly tells the solutions to go downhill. So you see this in this simple picture, the idea of this, the flow lines. And the point is that, so the typical example one usually provides when speaking about classical Morse theory is this tilted torus, where the function considered here is just this height. So you just put this torus standing on a table and you measure the height about the table. This is the smooth Morse function, and then it generates this these flow lines. Some of them are just marked here somehow. So this is a picture taken from Wikipedia. And the so there are many variants of course, of the Morse theory, but in terms of applications, the Morse inequalities are most important. So you look in the number of critical points. So the points where the vector field is 0, and of course you need several assumptions that the critical points have to be non-degenerate, so you can speak about stable, unstable manifolds there, and you take the dimension of the stable, unstable manifold. This gives you the Morse index. You count the number of points, and it turns out that the number of these points is not less than the ith Betti number of this manifold. So you recall from my previous talk that the Betti number is a topological invariant, which roughly speaking measures the number of ith dimensional holes in the space. So in case of torus, you have Betti number 2 in dimension 1, and it corresponds to 2 critical points, one here, with one-dimensional unstable manifold. So this is the direction of the unstable manifold. Sorry, here for the 2 points. Then there is Betti number in dimension 2 is 1. So this is just this repeller here at the top, and in dimension 0. There is one attracting fixed point in the bottom. But of course, you can represent, you can choose a different Morse function, or you can just reorganize this torus slightly so that there are more peaks, like for instance, something like here, like this here, and this is why you only get inequalities. Okay, so it turns out that, okay, so this, I already mentioned that last time, that actually there are a lot of application of the Morse theory which go in both directions. If you understand topology of the manifold better, then you may draw conclusions about the features of the dynamical system. If you understand the dynamical system better, you may draw conclusion about the topology of the manifold. But the big question is now, is it possible to do a purely combinatorial version of it? And Robin Foreman gave positive answer. He wrote a series of like 6 or 7 papers on this subject. Here are the main 2, his papers. They were both the very end of the 20th century. And I want briefly to present his main ideas, which will be useful for us. I only briefly mentioned the actual Morse theory, because more important for us are the concepts he developed to build this theory. So let me start with some notation and terminology. So we will work with simplicial complexes. But actually, the theory applies to more general class of CW complexes, so cellular complexes. But the simplicial complexes are probably most common and easiest to present examples. So the point is that I want to think about this simplicial complex as in this picture, as a finite object, in the sense that I'm not interested in all these points. So the picture is more a geometric representation of this simplicial complex. But for me, this simplicial complex is a finite collection of simplices. So I have vertices, 5 vertices. But apart of that, I have 6 edges. And actually, in my pictures, I'll mark these edges with small circles in the center of the mass, because we'll do graph theory actually with vertices associated to the simplices. So these centers of mass will serve us as the vertices of the graphs we will construct. And we have two-dimensional simplices. So again, I put a circle in the center of mass. So this way, I see this now as a finite object, a finite collection of simplices represented by the centers of mass of these simplices. Then I'll need the face relation or facet relation. So facet relation. So if I have sigma, if let's say tau is a facet of sigma, tau and sigma are simplices. If it is a face of sigma of codimension 1. So for instance, this vertex is a facet of this edge, and this edge is a facet of this triangle. But this vertex is only a face, but not a facet of this triangle. I'll denote the facet relation by, Oh, then I'll use the notation of the combinatorial boundary of sigma, of a cell sigma as the set of its facets, and dually a co-boundary of sigma, the family of cells rho, such that sigma is a facet of rho. So this is the notation I'll use. And this is the main concept introduced by Forman, the combinatorial vector field or discrete vector field, but I prefer, Forman used both concepts, combinatorial or discrete vector field. I prefer combinatorial. So a combinatorial vector field. By the way, I usually denote the whole simplicial complex by script K. And the vector field will be script V. So a combinatorial vector field V on this simplicial complex K is a partition of this collection of simplices of K into doubletons and singletons, but not arbitrary doubletons, but such that for each doubleton tau sigma in V, either tau is a facet of sigma or vice versa, or sigma is a facet of tau. Okay, so since one is a facet of the other in the doubleton, we can mark these doubletons by arrows, which point from the lower to the higher dimension. So this edge together with this triangle makes a doubleton, a correct doubleton. This vertex with this edge makes a doubleton. But there are some which are only singletons, some which are not paired. So this one, for instance, or this one. And the crucial thing is that I want a partition. So each simplex either is a singleton or belongs to precisely one doubleton. So this is the Forman's concept of vector field and combinatorial vector field. And I have to admit that when I saw it at the first time, it looked very strange to me and not convincing. But the beauty of this is with this simple tool, he was able to construct an exact analog of classical Morse theory, and he did not require any smooth manifold, and those of you who know how painful it is to make a precise definition what a smooth manifold is, with all these maps, atlases, and so on, this is I guess much simpler. And now, so this is just this is yet the combinatorial vector field, but here is also an analog of this discrete Morse function. So in general, this is just an integer valued function. So a discrete is an integer valued function which preserves so maybe I should have mentioned already here that when I have this facet relation, so this facet relation extends to a partial order, which I denote just the usual way. So just to phase relation. Phase relation for a simplicial complex makes it a partial order on this collection of simplices. So going back to this definition of discrete Morse, which preserves the phase relation, but with some exceptions. And this was another thing very strange at the first look, these exceptions. So in general, what I want is that the value at a face is smaller than a value on the simplex. So let's take this triangle. The value here is 14. Here is okay. The value at the edge is 12 is less. The same here, it's 10, it's less. The same here and here and here, but not here. This pair makes an exception. So let's mark all these exceptions. So we have an exception here. Another exception is here. One more is here. And so on. So here are, I think, all the exceptions now. And you see that these exceptions actually form a partition. So either something, a cell belongs to an exception, or is a singleton not belonging to any exception. So the precise definition is a little bit complicated, because maybe I write it just so that it's clear. So what are the exceptions? You define the, so let's say the function is f, which goes from the collection of simplices to z, and then you count the cardinality of cases of elements in coboundary of sigma, such that the order is not preserved. So the value at rho, it should be, since rho is, sigma is a facet of rho, so the value of at rho should be greater than the value of greater or equal, but actually an exception will be, it's just the opposite. And we request that the number of exceptions for sigma should be not greater than 1. And there is a dual assumption. Then you take now pose in the boundary of sigma, that now f of tau is greater or equal than n of sigma. And here there is at most one exception per each simplex. So for each simplex, when you go through the boundary, there is at most one element, a facet in the boundary, so that the value there is greater, not less. And the same when you go through the co-boundary, there is at most one element in the co-boundary where the value is less and not greater. And then you define a cell to be critical. Sigma is critical if it has no exceptions. So if both C plus of sigma and C minus of sigma are 0. So actually you can check that here we have no exception and also here we have no exception, but everything else belongs to this precise one exception. So you can redraw this. So here again, all these exceptions, and you can redraw this as a combinatorial vector field. And of course, you have to prove something, because it's not immediate from this definition of exceptions that you get a partition. But actually, this is what Foreman proves, that this is enough to prove that if you know only at most one exception, then when you take the pairs forming exception and singletons what is free of exceptions, you get actually a combinatorial vector field. So this is the typical way to draw it, not as a partition, but with these vectors and the circles surrounding singletons. And this is a picture taken directly from one of Foreman's papers, because when you read those papers, it's clear that Foreman's interest was not so much in studying combinatorial dynamics, but do the minimum he needed in dynamics in order to formulate the Morse theory. So he did not go too deep into the analogs, possible analogs of dynamical concept in his theory. Nevertheless, there is something like a solution of differential equation, namely what Foreman calls a path. So Foreman's path is a sequence of doubletons or vectors, because that's the alternative way to phrase it. By the way, my definition of the combinatorial vector field is not the original by Foreman, it's equivalent to it. It's more convenient for the needs of my present talk, but when you look into his paper, you'll see a different definition. At first sight, it may look even quite different, but then it's not difficult to prove that the two definitions are equivalent. So you have a sequence of doubletons. Let me denote the of lower dimension, but xi minus, that of higher dimension, but x of I plus. So the difference in dimension is just one. So this is a finite sequence of such doubletons such that the xi plus, so the higher dimension in the earlier doubleton, has as a facet the next one. So these in this example, these doubletons. So this is a center of mass. So this is x1 minus x1 plus, and x2 minus is actually, it's a facet of x1 plus of this, and so on. What is hidden in this concept is actually, I let myself to add something to Forman's picture. Namely, it's quite possible that you have more triangles here. So this was just to illustrate the path. But of course, the simplicial complex may be huge. So actually, in his path, when he went to this triangle here, then he chose to go to this face, but there is another face. And here there may be another vector. So he has options here. So when you pick up a cell, there are many paths which go through this cell like this, and also backwards. You can go here or you can go here. So there is hidden multi-valuedness in his concept. He does not mention that, but what actually, when you try to build something on top of his ideas, you are directly led to the multi-valued dynamical system on the collection of cells, which may be looked at as a directed graph on this collection of cells. So actually, this is something which may look strange at first, that we have to go to the world of multi-valued maps. But actually, it's not so difficult to realize that if you want to have finite world and classical maps, then the dynamics cannot be very interesting. If you want to regain the wealth of classical dynamics, you really need, in this finite world, multi-valued dynamics. So this is now something which is not present in Forman's work, or is present but only implicitly via this concept of path, because I prefer to reformulate his concept just as going through a directed graph. And I want to add extra arrows here. I refer to this arrow as implicit arrows. So this is a very small example with a combinatorial vector field, so 3 vectors and just 1 singleton. But the point is that so this is already like a directed graph, which tells me that I can go from here to here, from this edge to this triangle. But then it looks like I am stuck. But you can do you can try to do, actually not with this example, but you can continue here, yes? So you went along this vector, and then you have these choices to go here and here, and should be given directly as another arrow. So there are implicit arrows which actually go anywhere to the boundary except the cells where you came from. So this is what I call V-D graph associated with a multi-vector field. So the vertices are the cells of K, and this is why it's so convenient to just mark them as centers of mass, these vertices, so that there is just one point representing the whole simplex. And the edges are of 2 sorts. So I call them explicit, so given directly by V. So these are these orange arrows marked here. And then there are also implicit edges. From target cell of a vector in V to all the faces except the source. Of the vector. And there are also, so I have explicit, implicit, and also loops. Loops at every singleton. And typically, we do not draw these implicit arrows and loops just to keep the figure simple, because to understand the dynamics, all what you need is to know the combinatorial vector field. Then it's enough to understand how you add implicit arrows and loops, and you can treat it as a directed graph, and you can travel through it. So before I leave the Morse theory, let me just quickly formulate what result Forman obtained with this theory. So first of all, it's clear that not every combinatorial vector field will correspond to gradient dynamics. For instance, here, once we understand how we move through this directed graph, so there is clearly a periodic solution here. You can go along explicit arrow up to this triangle, then you use implicit arrow to go down, again explicit, implicit, and so on, and you come back. So you can travel here around. And of course, in the gradient dynamics, there should be no periodic solutions or any other recurrent solutions. So actually, theorem by Forman says that, so this was Forman 1995, that a combinatorial vector field. So I start now, for instance, with this one, and I want to ask whether it comes from a discrete Morse function or not. So this vector field is the gradient vector field of a discrete Morse function. If and only if this VD graph is acyclic. So not this one, because here we have a cycle in this directed graph, yes? Of course, I did not say precisely what this gradient vector field of a discrete Morse function is, but this is precisely this construction. Let me go back here. Once we have this discrete Morse function, we have this set of exceptions, and then Forman's theorem that this set of exceptions together with singletons which do not belong to exceptions form a combinatorial vector field. This is exactly the gradient vector field associated with the discrete Morse function. So the reverse criterion comes directly through the study of this directed graph. Forman formulates it a little bit different via his paths, because all he needs is this concept of closed trajectory here. But this is equivalent formulation. Okay, and now very briefly, his theorem, which is an analog of the classical theorem. There is one, so there are several analogs proved by Forman. The one which is best for computational mathematics is based on the homology theory, because homology, which I explained last time, leads directly from topology to linear algebra, and it's easy to make linear algebra computations. And this result, based on homology theory in Morse theory, says that you can construct a Morse complex. So this is an abstract chain complex, Morse complex. So it consists of the collection, so let M be the set of critical cells. So in this case, only those three. And then you need a boundary operator such that the basis of the Q chains is just the collections of critical cells of dimension Q. So instead of taking the dimension of the unstable manifold as in the classical theory, every cell has its natural dimension. So a triangle is two-dimensional, the edge is one-dimensional, the vertex is zero-dimensional. So here M2 consists only of this, M1 of this, M0 of this. And then the boundary operator, the matrix of the boundary operator is given by a formula that the boundary of a cell, critical cell sigma, with respect to tau, the entry in the matrix, is given as the sum of so-called weights of alpha, where alpha is a path, Forman path from sigma to alpha. This weight is actually the simplest, it's just one. If you take the two coefficients, in the more general case, you have to multiply certain incidence numbers. But for Z2 coefficients, all incidence numbers are 1, so the product of ones is just 1. So you just look how many paths, Forman paths, go from, for instance, from here, from this edge to this vertex. There is one path this way and another path this way. So, so here is an implicit arrow which lets you go down to the boundary. Then you take explicit arrow, again implicit arrow. So there is one path and there is a symmetric one here. So since there are two paths here, actually the addition for Z2 coefficients gives you 0 in this sum. So this boundary operator is 0 and gives you directly the homology of the this simplicial complex, which is trivial. But the theorem, which is the analog of the classical theorem of the Morse theory, is that the simplicial homology of this simplicial complex is isomorphic to the homology of this abstract simplicial complex constructed of these critical cells and this boundary operator. And in particular, this implies these Morse inequalities. Also in this case. So in practical terms, this means that the number of critical cells must be at least the Betti number in the same dimension of the simplicial complex. Okay, so let's now go further in the direction of Conley theory in this setting. So I need to introduce some more concepts in dynamics based on this combinatorial setting. So I define now an analog of a solution of differential equation, a partial map gamma from integers to the collection of simplices. By partial, I mean the domain need not be the whole Z, although the most important case is when the domain is the whole Z, but sometimes some smaller domains are useful. So such a map is a solution of this combinatorial vector field if it is a walk in the V digraph, which means that gamma of I plus 1 belongs to the, what I denote PV of gamma I, where this is the collection of targets originating in gamma of, sorry, this, as long as both I and I plus 1 are in the domain of gamma. And then a full solution, if the domain is the whole Z, I speak about the full solution. And if the domain is an interval on integers, I use the graph terminology, I speak about the path. So do we have in this example a full solution? not in this one. But when we go back here, yes, there is a full solution. You can just, because you remember in the VD graph, every critical cell has a loop, which is implicit, not marked here, but it means that you can keep standing here as long as you wish from -infinity. And at certain time, let's say at time 0, you decide you are bored in standing. So you now decide to take your choice, because another option instead of standing here is to take this implicit arrow down to this vertex. Then you have no choice but to continue here and no choice again. And once you end up here, you have no choice but to use this loop, which is here, to stay here up to infinity. So this is a full solution here. But of course, we can also speak about the path. We just starts here, goes here, 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 and then here. Then it's a finite path. The concept of path is just useful to in certain definitions to simplify the definitions. Okay, so once we have the definition of a path, there is a question about the invariant sets. So you can define the set of solutions through a given cell X sitting in a subset A as the set of all full solutions from Z with values in A. A is a subcollection of cells, such that you pass through zeros, through X. So let's say at 0, the value is X. So this is the set of solutions, and then you can define the invariant part of A as the collection of X's in A such that the set of solutions is not empty. So there is at least one solution in A. And we say that S subset K is invariant if it is equal to its invariant part. So do we have what invariant parts, invariant sets do we have in this example? For instance, clearly every critical cell in itself is invariant, because you can have just a constant solution. You have this loop here implicit, so you keep sitting here. So every critical cell is invariant. Do we have something else? Yes, we have this periodic orbit here, maybe. So the collection of these cells, maybe let me use a different color. These 6 cells form an invariant set because there is this periodic solution, which you just keep going infinitely many around. And there is one more, another color, which is also periodic. One here, again, 6 cells. We'll see that actually this one is repelling and this one is attracting. The formal definition, I hope I still manage to present it today, we'll see. But the intuition is very clear. Once you can come, for instance, you can start here at this critical cell. You can stay here from -infinity to 0, and then you decide to go to take your choices. So you go down to a phase, and then you no longer have choices. You are just trapped here. So this is an attractor. Once you reach this periodic orbit, you cannot escape. But with this periodic orbit, it's vice versa. You can go around infinitely many times, and then you may decide that you are bored, and then you have choices. You can go, for instance, here to this critical cell, and this is again an attractor. You are stuck here. But you can also go, for instance, here, then you are forced to actually reach this periodic orbit, and you go here around. Okay, so we have invariant sets, but you remember that the Conley index is not defined for an arbitrary invariant set, but for isolated invariant sets. So the big question is there a way here to distinguish between invariant sets which are not isolated and invariant sets which are isolated? This was a big puzzle to us, and first realization that actually the very first concept was very wrong. We thought everything is finite, everything is combinatorial, so maybe every invariant set is isolated. But this is wrong. And it took us time to realize that also here we need the concept of isolation. But this isolation is a little bit strange at first again. And to explain why it's a little bit strange and what needs to be modified, I need an interlude about finite topological spaces. Namely, I already said that I treat a simplicial complex as a finite object, and actually you can treat it as a poset. I already mentioned that, but here this simplicial complex is drawn directly as a poset. So you have the two triangles here at the top, then the 6 edges, 3 of one triangle, 3 of the other triangle, and then the vertices at the bottom. This is, and of course, as in the Hasse diagram, you draw the poset with edges going from the larger to the smaller element. And there is this concept of upper sets in a poset. A subset K is upper if I have an X in A and an element which is greater or equal to X, then this element must also be in A. So for instance, an example of an upper set here, for instance, this is an upper set. And for instance, when you take this, then this is not an upper set, because here this element is above an element in the set, in the red set, but itself is not in the red set. So the red one is not an upper set, the green one is an upper set. And it turns out that the family of upper sets in a finite poset forms a T0 topology on, let's call it X. No, sorry. So this applies to any poset, any finite poset, but we think in terms of our simplicial complex, because the labels come from the simplicial complex, so on K. It's called Alexandrov topology. You may not remember these separation axioms from topology course. So very briefly, T0 topology means that it's not Hausdorff. The Hausdorff topology is like in the metric spaces. If you have 2 points, then you can always find 2 balls centered at the 2 points, so they are disjoint. But in T0 topology, this is the weakest separation axiom, and it only says that if you have 2 different points, then there exists an open set such that one point belongs to the open set and the other point does not belong to the open set. But you have no choice which is in the open set, which is not. So this is the very weakest separation axiom you have in topological spaces. And actually, very briefly, if somebody is interested, so I just keep it printed here. If you start with a poset, so a set with a partial order on it, when you take the family of upper sets, you get a topology, but you can do also the reverse operation. When you have a finite T0 topological space, then you can define a relation by taking X in the closure of Y. Again, a surprise, because typically we think that the closure of a singleton is the singleton, but this actually follows from this Hausdorff separation axiom. If you do not have done that, then the closure of a point may be bigger than the point. And actually this then produces a poset this relation. And Alexandrov proved in 1937 that actually there are functors. He used a different language, but with present-day language of category theory, there is a functor from the category of ordered spaces to the category of finite topological T0 spaces and vice versa, and these are mutually inverse functors. So actually, this in practice means that the theory of T0 finite topological spaces is the same as the theory of partial orders, which gives you a lot of flexibility because there is a lot of algorithms for posets, and you can translate every problem in finite topological spaces to poset theory problem. But for us, there are just one important lesson is from that. So I already mentioned that we can only assume T0 separation. It's easy to prove that if a finite topological space is T1 or in Hausdorff, then it's just discrete, so not interesting. So only T0 separation makes sense in finite topological spaces. Then every set is compact, trivially, because everything is finite. But most importantly is that compactness does not imply closedness. You may remember from topology the theorem that the compact set is always closed, but this again uses this Hausdorff axiom. In terms of the Conley theory, it's important that you have homology theory. The singular homology theory makes sense and is actually computable in finite topological spaces. But for us, this is the most important observation, that is isolated invariant set in combinatorial setting are not closed in general. We've seen these examples in the classical Conley theory of isolated invariant sets, and they were all closed because they were all compact. And actually, you cannot make this assumption in the finite setting, because then everything falls apart. You'll see this in a moment. Very briefly, I mentioned that this homology theory is defined in finite spaces, and there is McCord theorem, which actually lets you make computations, because with every finite topological space interpreted as a poset, you can build an abstract simplicial complex, and the homology of this abstract simplicial complex is the singular homology of this finite topological space. So in terms of computations, we are in perfect shape when we treat a simplicial complex as a finite topological space via the poset of faces. And the last thing from this world of finite topological spaces we will need, there is a dictionary. I already mentioned that everything via this Alexandrov theorem, we can translate everything from finite topological spaces to posets. So in particular, open sets correspond to upper sets. You can guess that there is a dual concept of downset, and this corresponds to closed set. There is also correspondence in terms of connectedness, but for us, a concept rarely used in topology, but very important for us, is locally closed. It corresponds to the order convex concept for finite posets. So here is the definition. A is locally closed if what I denote mo, and this is shorthand for mouth, of A defined as the closure of A minus the set itself is closed. And so this is in case of the topological spaces. And if A sits in a poset, then A, its order convex. If when you have the situation that Y is sandwiched between X and Z, which are both in A, then Y must also be in A. So these two concepts correspond to itself in this Alexandrov correspondence. And this is useful for applications. Okay, so we can go back to combinatorial dynamics now, and I hope now these ideas will be less strange at first. But before I do that, I also need an extension of the concept of combinatorial vector field by Forman. Namely, as I already mentioned, Forman was interested just in getting the analog of Morse theory in his combinatorial setting. He was not very deeply interested in dynamics itself. But when you think about modeling classical dynamics with these combinatorial tools, you immediately see that there is that the tool may be not sufficient. Think about this classical saddle flow around this fixed point here. And imagine that we discretize the space. Just for simplicity, this time as I take not a simplicial complex, but a cellular complex with cell consisting of squares. But you can do the same example with triangles. It's just the picture is slightly more complicated. And you see the same problem. So the problem is not that we switch from triangles to squares. The problem is that somehow here it's natural to think that, okay, so if my combinatorial space consists of these cells of this cellular complex, then this edge should be paired with this square because the flow goes in here. So it's natural to expect this behavior here. But when you go, for instance, here, then actually you would tend to say that all these edges should go inside this square. So I'd like to pair all these three with this cell, but you remember we need a partition. So if you just do the vectors like this, this, and this will no longer be a partition. And the remedy here is actually to extend the concept of combinatorial vector field to the concept of multivectors. So instead of keeping only singletons and doubletons, allow also subsets of larger cardinalities, so not necessarily just one or two. In this case, I'd like to just make just one group out of all these cells. This vertex, this edge, this vertex, all this together. So, but it's more important for me to keep a partition than to keep just singletons and doubletons. So here is this picture redrawn in the combinatorial fashion where I have my multivectors. So this collection of cells is a multivector. This is a multivector. This is a multivector and so on. This is also a multivector. But the point is that I do not want an arbitrary partition. I do need an assumption about what will be my multivectors. What is the assumption? It comes from the observation that singletons and doubletons in combinatorial vector field. So this Forman concept are actually convex. And they are almost trivially complex. Singleton, there is no way to put anything between singleton and itself. It's only itself. And doubleton, it's not an arbitrary doubleton. The condition that one is a facet of the other exactly means that we have two cells and nothing in between in terms of the phase relation. So they are trivially convex. So using the topology language locally closed. So our definition of combinatorial multivector field is a partition of K into locally closed sets. Or convex using the poset language sets. So here is an example. You can check that this one is locally closed. Why? When the closure operator for finite topological spaces is just taking everything which is in the boundary, regardless of dimension. So when you take the boundaries of all these cells, all what you'd add is this. And this itself is closed because there is this vertex has just itself in the boundary. This vertex has just itself in the boundary. This edge has this vertex and this vertex in the boundary. So when you take the closure here, there is nothing added. So the mouth of this multivector is closed. So this makes it really a correct multivector. Okay, so we continue with the concept, and I'll make now one modification with respect, because in general, the concept of solution, everything is the same, but for reasons I have no time to explain, we decided that once we switch to multivector fields, it's convenient to redefine this D graph. So the way I define now the D graph, I allow actually a little bit more implicit arrows, namely, I can treat this as a directed graph, but also as a multi-valued map. So this FV just tells me what are the successor in this directed graph of a given cell. So given a cell X, I say that I can go anywhere to the closure of X, so to the boundary of the cell, but I can also go anywhere to, and yes, this notation, sorry, I should have given this first. So let's make place, denote by, so if I have a cell X, then since my multivector field is a partition, there is a unique multivector to which X belongs. So this is the unique multivector to which X belongs. And now this is my new definition of VD graph. Actually, with this definition, everything is invariant, which may be strange, but actually for reasons I have no time to explain, it's not a big problem because we introduce, and I hope I'll manage to do it in a moment, we introduce the concept of essential invariant sets. So these are the essential invariant sets. So everything will be invariant, but we'll be just looking into essential invariant sets, which will really matter. But other things are a little bit simpler. So this is the difference, is that if we fold precisely the previous idea, whenever we have a multivector, we would be only allowed to go up in dimension, but actually this implicit arrow should go only to the other places in the boundary of the cell, but not to the places where we came via multivector. Here we actually allow to go back to any face in the boundary, which means that actually you can do a solution which goes like this: up and down, because you can go anywhere within the same multivector. So in some sense, I treat this as a kind of multivector, as a kind of black box where I know nothing about the real dynamics. So I do not want to forbid something. So just it's better to allow more than to forbid something. So I say, since I do not understand what's going inside the multivector, I just allow for any movement. And here I just say that since I think about modeling something, and I believe there is some real flow which I try to model here, which goes here through these cells. So whenever I go from a cell to another cell, I have to cross the boundary anyway. So this is why I allow to always to going to the boundary. So the point is that the multivector is not closed, which means that sometimes you can go in one direction, but not back. because look, you can go here, you can go back to the boundary, but you have no way to continue into this multivector because this cell does not belong to this multivector. So, and you can go only within the multivector or towards the boundary. So this is not very useful. You can just struggle here, trapped inside in this multivector. You have a chance to continue to the mouth of the multivector, but not to the mouth of another multivector. So it turns out to be working pretty nice in practice, this modified definition. One more concept which I'll need in a moment, I say that a subset is V-compatible if has the feature that if a multivector intersects in a non-empty way A, then actually the multivector is contained entirely in A. So in other way, a V-compatible set is just a union of the multivectors it contains. Okay, you notice, because I accidentally moved to the next slide, which is a bit unusual. So this is just a mountain chain in Sierra Nevada in Spain. But the point is that I mentioned here gradient dynamics, and gradient dynamics is going downhill. So actually there is a nice interpretation, very intuitive interpretation about these multivector fields and its dynamics. You should think about this simplicial complex the way that actually the top dimensional cells, so when you think about something two-dimensional which would correspond to the surface of Earth, then the triangles are actually mountains. So every triangle is a mountain, like in this picture here. Every vertex is in a valley, and every edge is a mountain pass. So you cross from one valley to the other valley between two mountains through a mountain pass. And you should think about the multivectors as just building lifts. So a skier, a lazy skier who is only ready to go downhill using the natural forces of Earth, once ends up in a valley, has no way to continue skiing down. But if there are lifts, then these lifts, so you can think now that every mountain here, it's like a cell, a two-cell, so that in the two-cell you can go anywhere to the boundary, and you can just reach maybe a pass, but from the pass, there you have still a one direction when you can go down and go down up to the valley. But then if there is a lift, then this lift lets you go up again. So this actually, via building this lift, so it's like you have this natural gradient dynamics of the manifold or simplicial complex, but these vectors or multivectors are like lifts which let you go up again. Okay, so let's go back to this concept of isolations. We are now ready to explain what do we need to explain what is really an isolated invariant set. And this is related to the thing which I, again, have no time to explain in detail, but we have a theorem. It was quite a lot of work to get it proved, that when you have a just vector field like here, so in this example, I again have only vectors, then actually you can now take the geometric representation of this simplicial complex, and you can build here a classical flow which somehow mimics the behavior of the dynamics here. So we have here 1, 2, 3, 4, 5 critical cells. So I have 5 stationary points. This one is repelling. So this one is also repelling. This is a saddle. You can come from here to the saddle, but from the saddle you can go to the vertices, and this is again a saddle, and so on. And now imagine that I want this collection of these two cells, so two singletons, which are clearly invariant, even in the previous meaning, they are invariant. If I want to treat them as isolated invariant, the counterpart in my this analog for flows would be like making an isolated invariant set something which contains. Sorry, in this example, I take more. I take also these fixed points here, so 4 fixed points. It's still invariant. So I want all this here. And if I want to make this isolated invariant here, and I'm looking for an isolating neighborhood, for instance, this one, you see that the isolation is violated here and here. And the same happens even if you enlarge it somewhere, there will be again a tangency here and here. So this, once we understood that we can just get some intuition via looking what happens in the counterpart in the classical setting, that gave us hints what should be excluded here. And the first hint was that actually the isolated invariant set should be locally closed. This one is not, because look, we want this triangle in the invariant set. This is a face of it, but we do not take it, this face, into the invariant set, but we take this vertex. So this face is a face of this triangle, but its vertex is the face of this edge here. So this is precisely which makes this collection not convex. This element is between those two in the face relation, but does not belong to the candidate of an isolated invariant set. There is one more thing which makes troubles here. And here is another example where I want the collection of these cells to make an isolated invariant set. They are invariant even in the previous meaning, because no problem at the vertices. And if you treat this as an invariant set for this cell, there is a full solution. You stay here from infinity, then you can go down to the boundary and continue to the vertex and stay here for infinity. So this is invariant even in the previous setting, but the associated flow looks like this. So again, when we try to make this collection isolated invariant in the classical setting, we see the trouble here. There is again an internal tangency. And the lesson we take from this is that isolated invariant sets should be V compatible. So the union of the multivectors. And actually there is a nice way of defining isolated invariant sets, but we went through these examples before we realized how this should be set up. So now we defined it in a way which resembles better resembles the classical definition. Namely, as I say that a solution gamma, a full solution to the closure of S is an internal tangency to S tangency to S if for some N1 less than N2 less than N3, we have gamma of n1, gamma of n2 in S, but gamma of n1 and gamma of n3 in S, but gamma of n2 not in S. So an internal, so if I have an invariant set such that, like here, that I have a solution which starts, so remember my candidate here for the invariant set is isolated invariant set, which turned out not to be an isolated invariant set, is the collection of these cells. So now when I start here, so in my set S, I can go down, which is in the closure of S. The whole edge is a closure in the triangle, so in the closure of the whole S. So I go down, then I go down here, and then I go up along this explicit vector, and I continue to this vertex, and I stay here. So this is a full solution which starts in my candidate for isolated invariant set, which stays all the time in the closure and ends up again in the invariant set, but goes from something which is not in the invariant set. So this is not isolated directly from this condition. And you can actually find the same here, that there is such a solution in this example. So we can prove actually the following theorem. An invariant set as is isolated. Sorry, first the definition. So I need the internal tangency to define what is now an isolated invariant set. So I just want to exclude internal tangencies as an invariant set, so definition. An invariant set S is isolated if it does not admit an internal tangency. And a theorem says that actually an invariant set is isolated if and only if precisely the two conditions I mentioned earlier are satisfied. S is locally closed and V compatible. So the definition is more or less mimics the classical definition because there are equivalent versions of defining. But I already showed that when I explained Warzewski set, that this internal tangency is not allowed if you want a Warzewski set. And to have an isolated invariant set, you need just a Warzewski set, which is a neighborhood of the invariant set. So this is in the spirit, this definition is in the spirit of the classical definition. And this theorem is useful in practice because this gives you a very elementary combinatorial criteria, how to check whether your invariant set is an isolated invariant set or not. Because for this definition, we would have to go through all the full solutions. And here it's just a finite computation actually to verify this. So let's look into our example. For instance, now we already had such a periodic orbit here. So this is an isolated invariant set because we've seen that already here. So what is the closure of this collection of cells? This is again a cellular, not a simply short, but a cellular complex with cells, two cells being just polygons. So here, what is the closure of this? So this collection of cells is not closed. What is in the closure? all these cells here and also this cell here. So now when I choose to go away, I can always take the path, for instance, here. And then once I'm here, I'm stuck. There is no way to go away. So I cannot come back to our solution here. The same when I choose here, then I can go in many ways. I can continue, for instance, here or here, but you can check that again, there is no way to come back to our invariant set, periodic invariant set. Actually, there is no way to come back just because this is an attractor, but here is this is a saddle, so you can come from the periodic orbit to the saddle, and from the saddle you can continue to another periodic orbit, which is here. But still, this is an isolated invariant set. So either when you in backward time come here, so in forward time you can not start from here and go into this orbit so that again to come back here. So there is no way to construct internal tangency. So this is a saddle, but still an isolated invariant set. As you can guess, I will not give a precise definition of attractor and repeller, or only mention, so you can define them similarly as in the classical case. But there is a nice characterization of attractors and repellers in this combinatorial setting. A is an attractor if and only if A is a closed isolated invariant set, and the dual theorem, you can guess A is a repeller if and only if A is an open isolated invariant set. So surprisingly, once we departed from the idea we originally tried to carry over from the classical dynamics that the isolated invariant set should be closed, once we accept the fact that in the combinatorial setting, because of this very poor separation axiom, which makes things very tight in finite spaces, you cannot assume that an isolated invariant set is closed, but instead, actually, you get purely topological characterization, what is an attractor, what is a repeller. Okay, and the very last thing, and I'll stop here, is just now we are ready to define the Conley index. So actually, you define the concept of index pair, which is a kind of counterpart of Warzewski set in this combinatorial setting. But when you study more the classical Conley theory, the concept of index pair is already there. It's more technical. It's needed not to define things. So typically it does not appear in a short overview of the Conley theory, but it's needed in proofs. Here, it's actually, I could also avoid mentioning this index pair, but it's the closest thing, at least to the Warzewski set in the combinatorial setting. So a pair of pair P of closed subsets of our cellular symmetrical complex K is an index pair, for an isolated invariant set S if there are three conditions. If X is in P2 and Y is in P1, but also it's a target of an arrow, explicit or implicit, so belongs to this multivalued map FV of X, then X must be actually in P2. So this is a kind of the analog of the exit set, but it's now thicker. The other condition is not present in the Warzewski set, but is the consequence. No, sorry. This is what I write right now is the analog of the exit set. If X is in P1 and there is something in a target which is not in P1, then actually X must be in P2. So this somehow corresponds to the exit set. P2 plays the role of the exit set. And this is just needed. This is not, has no analog in the Warzewski set, but this is just needed because P2 is not a part of, not necessarily a part of a boundary. It may be a bigger set. And the last thing is that S is just the difference or the invariant part of P1 with P2. It depends whether we choose the broader way of defining implicit arrows as for multi-vector fields or the narrower one as for the when I started. And now how do you define the Conley index? You have the theorem. Very exact counterpart of the classical theorem on which the definition of the classical Conley index is defined. For every isolated invariant set, S, there is at least one an index pair. This is one, and two, if PQR index pairs for S, two different index pairs, then the homology, relative homology of one pair is isomorphic to the relative homology of the other pair. So this gives now the definition. The Conley index of S is just the homology of an index pair. There is one, and you can choose any because you get the same homology. Okay, so this way we reach the definition of the Conley index in the combinatorial setting, and I think it's high time to stop here. In the last lecture, I plan to speak about the tools built on this theory, which you hopefully might use in data analysis, in machine learning. So the concept of Morse decomposition, the concept of Morse-Conley graph associated as a stronger invariant for the Morse decomposition, and then how you look into the persistence of such things, in particular, but the persistence of the Conley index. So things like that. So thanks a lot for your attention.
Yeah, thank you very much. Thank you. Any questions or comments? Yeah, I guess not. Yeah. Okay. Thanks again, Marian. And again,
I wonder,
yeah. Okay. Do you have the question?
I wonder this beautiful picture that you used as an example so many times. It started with some parallelogram in the middle, and then there was a bit of hex.
This one?
This one, it's a lovely picture. And in my wild imagination, may I say that it is a projection of a toroid? And if so, there is room to interpret all these pictures and cycles and so on in 3 dimensions.
Actually, I just use 2-dimensional examples because it's easy to draw pictures, but all these concepts make sense in arbitrary dimension. And actually, I do have even some pictures in 3D where you construct these combinatorial multi-vector fields. And we work now on applying these methods to actually get computer-assisted proofs of chaotic dynamics in 3D. And the proof goes through the construction of these combinatorial multi-vector fields on a triangulation which is transversal to the flow lines. And this is actually what we construct is a combinatorial multivector field in 3D.
Okay, beautiful. Thank you.
All right. Okay, thank you. Are there another question or comment?
I have a question.
Yeah.
May I?
Yes, sure.
Yeah, please go ahead.
Yes. Okay. I think, thank you for a nice talk. How would you apply this to a stochastic differential equation?
Great question, but for the moment, I'm yet far from that questions for two reasons. One reason is very simple. I do not know yet how to do it. The other reason is that I need really a collaborator to go in that direction, because my mind is not good in working with stochastic problems. Nevertheless, what I can say right now is I have a colleague of mine who works right now with classical tools from Conley theory in the stochastic setting. And he gets quite nice results. And I already spoke with him, and he thinks that actually he already started with my PhD student on a possible combination of the method he uses via the classical Conley index with the methods we use in this combinatorial dynamics. So since, as I said, I'm not a good person to answer questions about stochastic dynamics, because this is something I never had a good understanding of, probably because of the construction of my mind. I believe people who work in this have just these beautiful minds, which I just envy that I not have one. But from the colleague who is good in that direction, I see that he understands how to do it. So at least there is some hope.
Just a comment here. I thought that this formalism accommodates implicitly noise because of persistent homology is defined as something that is persistent under noise, right? So
yes.
So it seems to be like I mean, I like this question as well, but so I mean, isn't it like doesn't it seem to be like a natural?
Yes, so this is what I plan to explain in the next lecture, that yes, all these tools concerning persistence from classical PDA may be adapted to this setting and used to study understanding what really the Conley index is in the presence of noise, for instance.
Yeah. So the extension, is not like not natural. It seems like a natural question to extend this framework to random dynamical systems, at least with small noise.
Yes, but still, so I'm not able to explain again, for two reasons, a lack of time, but also lack of my real understanding. But what my colleague does, Bogdan Batko, with Konstantin Mishaykov actually right now, is a very clever way on building some stochastic analysis on top of these tools, which look at first like completely not stochastic. So this is all what I could say at the moment, but it was a big surprise to me that you can do something like that.
Yeah, okay, yeah, thank you. Yeah, all right.
Okay, thank you.
Okay then. Okay, thanks again, Marian, and everyone who attended.
Thank you, Boubedian.
And happy holidays, and see you next year, I guess.
Yes, happy holidays to all of you.
Bye-bye. Take care. Bye.
Thank you.
Bye.